your pH level is an indicator of how full your soil's capacity to hold cations is. So your cations are your positively charged elements, and pH is the inverse log function of the hydrogen ion concentration. So as your soil's capacity to hold nutrients is emptied, then hydrogen takes its place. And hydrogen, in this sense, is just the ionic form. It's just the proton, not the electron. The electron is in the electron cloud. It's wherever it is out there. Somewhere in the universe, you can bet there's enough electrons to balance all the protons. But we don't know just exactly which electron or anything like that. It's very broad. But the proton is there. As the pH drops, then the hydrogen ion is and it increases logarithmically as you go from 7 to 6. In other words, 6 is 10 times as many hydrogen ions, and 5 is 100 times as many hydrogen ions, and so forth. So you've got a pH that's up here very close to neutral, and that means that your cation exchange capacity is pretty close to your total exchange capacity. So what you see here at the top of the test, cation exchange capacity, is 10.59. Your total exchange capacity is 10.75. So your cation exchange capacity is very close to your total exchange capacity. At pH 7, they are the same. So to see what you've got in your cation exchange capacity, in other words, those things that are attached to your clay colloid or your clay humus complex, will have a different, there's different proportions of things. So in your soil here, 74% of your cation exchange capacity shows up as calcium, and 19.53% shows up as magnesium. So you're rich in calcium, and you've got quite a surplus of magnesium in your cation exchange capacity. But potassium here is only 1.93%, when it could be up here between 3 and 5 if it was adequate. So what we want to look at here, these numbers here on the soluble test, the Albrecht test, are what relates to your base saturation, the saturation of your bases or your cations. And it doesn't tell you what the total is. So this says calcium is 1,609 parts per million, which is more than the target, which was 68%. And yet over here in your total, you have 26,000. You have another 10,000 parts per million that don't even show up as exchangeable.
Soluble.
They don't show up as exchangeable, so they're not soluble, so to speak. In other words, water, if it got in there, wouldn't exchange for it and give it hydrogen. So you want to look here, if the potassium here is so low, how much potassium do you actually have? And you do still have considerably more potassium here Well, no, you don't. Okay? So potassium here is 81 parts per million. Here it's 827 parts per million. So you have more than 10 times as much potassium in your total as you have here in your exchangeable. And when it comes to sodium, let's see what that one shows up. Sodium is very high. So it's got 51 parts per million where it would be fully loaded at 37. And you've got 184 parts per million in your total. Now those are your four major cations. You would like to get them into this relationship here, the target relationship of 67% calcium, 13% magnesium, maybe 5% potassium, and 1.5% sodium. And aluminum here takes some place in that because there is theoretically exchangeable aluminum in any clay, because clays are aluminum
Mostly,
silicates. Yeah. But when you look at a particle of clay, even though it's colloidal, so it's down there at a very low diameter, it's still billions of atoms. And so it has an aggregate charge that allows it to hold on to exchangeable layers of cations. And that encourages the humic acids to sort of slime onto it and form complexes. And when that happens, when the humic acids form complexes with the clay, then the cation exchange capacity goes up considerably.
Say it again.
So when the humic acids form complexes with the clay particles, then the cation exchange capacity goes upwards very significantly.
Okay.
So what you want to do is to have those humic acids forming complexes with your clay particles, because what happens after the cations hold on to the clay particle, it still forms several more shells or layers of water that it holds on to. So when the clay gets wet, it holds on to water. It holds on to a very large amount of water. But with the humic acids, it holds on to multiples more. So you want to get your soil, and this is true of every soil, you want to get it to form those clay humus complexes. And that was the idea behind the compost pile that we were building at Cliffs.
Adding the clay.
Yeah, adding the clay to that, then, and adding your clay from your farm to that is a way of patterning the way you activate the whole clay throughout your whole system. So by the time you get that compost made, that compost pile should be so potently attuned to Cliff's farm that it wakes up. He's got heaps and heaps of phosphorus and zinc that are not showing up in the growth of things. But by putting his clay in his compost pile and activating it, then the clay becomes the most important thing he put in that compost pile, because it will have the pattern of waking up the phosphorus and the zinc. And so every place he puts that compost is going to wake up the phosphorus and zinc. See what I'm saying?
Yep.
So instead of raw humates, if you can make even a small amount of compost with this idea in mind, and use it very sparingly even, then it's more like what you're doing is you're feeding the resonant energy that you want to achieve on your land.
It's like a homeopathic thing.
Yeah, only it's somewhere in between, like the homeopathic dilution and the full-on substance application.
Okay.
But you see where I'm coming from with that.
Yeah.
we want to achieve that kind of activity. Let's see what you've got here that shows up deficient over here. Manganese deficient over here is 5.1 parts per million. Manganese over here is 324 parts per million. So you have quite a fair bit of manganese that's not working. In other words, 5 into 324 is going to be 64 times more here than you had over here is available. Your boron over here, it wasn't given. It was very low, I take it. But over here, maybe it was quite a bit higher. Various things like sulfur is the catalyst, and it's the sort of thing where when I'm giving recommendations, then I try to see that you actually put the sulfur there, like as gypsum maybe, or as elemental sulfur, so that you're actually applying some sulfur. It doesn't have to be a full hit, but you can see here that if it comes to nitrogen to sulfur ratio, which ought to be about 6:1, then you have 12:1. So you really need to build sulfur into your system.
Right, and
that will expose the surfaces of things, and it will allow a lot more release of nutrients.
Yeah, we're using both gypsum and elemental sulfur.
Okay, yeah, well, you probably need to. Those two are needed here. I'm happy with low nitrates and low ammonium. That's a good thing. Your phosphorus at 178 is really surprisingly high, because over here you only have 322 parts per million. So I'm wondering, how in the world did phosphorus get so high?
Maybe compost?
Maybe compost, yep. Compost has a tendency to do that. Silicon at 36 parts per million is below any target range that I would have looked for. And over here, it's not much higher. 125 is not very high at all. Look at copper, 0.8 of a part per million. Copper has to be present for phosphorus to function properly, because phosphorus is able to accept electrons and be in a higher energy state, or give off electrons and be in a low energy state. But it needs copper as its connection to transfer electrons. So without copper as a cofactor, then it neither receives or gives off electrons. So it requires that vibration of copper in order to work. And in the winter, when the temperature is low, like at, say, 32 degrees, copper works 100th as well as it does at 90 degrees. Because on a Celsius scale, then for every 10 degrees Celsius, copper works 10 times as well, or going in the other direction, 1/10 as well.